Today we will be discussing about relative motion. A relative motion means, say there are two trains moving, right, or two cars moving. Suppose this is car A moving with a velocity of 10 meter per second, and there is car B moving with a velocity of 3 meter per second. Then with respect to car B, these two are moving at these speeds with respect to the ground frame. With respect to someone standing on ground, velocities of car A is 10 meter per second towards right, and velocity of car B is 3 meter per second towards the right also. So relative to A or relative to B, let's see the situation. When I am saying relative to B, that means B becomes the reference frame or frame of reference or frame of reference or the observer. So if you look at from the viewpoint of B, then obviously what is the velocity of A? Then velocity of A is 7 meter per second, because you know this VA, this 3 meter per second, that is VB equal to 3 meter per second, and VA equal to 10 meter per second. Now this becomes the reference frame or observer. Then with respect to B, this car A travels at a velocity of 7 meter per second. So this velocity of A with respect to B, velocity of A with respect to B, with respect to, I can write like this, WRT, with respect to, okay, velocity of A with respect to B is given like this, VA/B equal to VA minus VB. VA/B is VA minus VB. So here you see VA with respect to B, B is the reference, that is why with respect to B. So here I will substitute for VA as 10 and VB as 3. So this becomes 7 meter per second. In the same way, if you observe from A, then what will it be? Velocity of B with respect to A, or it is the relative velocity, relative velocity of B with respect to A, or you can write velocity of B with respect to A. Same thing, velocity of B with respect to A, or velocity of B relative to A is VB/A, like this, equal, it's VB minus VA, and I have taken here the right direction as positive. So VB is 3 and VA is minus 10, so it becomes minus 7 meter per second. That means if you observe from A, then see, if you observe from A, then obviously A is at rest. Whatever is the reference frame, that is at rest with respect to that reference itself. So now, as with proper signs, what has come? VB with respect to A is minus 7. That means here it is 7 meter per second towards the left. This minus 7 means 7 meter per second towards the left. So that is the meaning of the negative sign and relative velocity. So if you are someone sitting inside the car A, then you will see B moving backwards at a velocity of 7 meter per second. And if you are someone sitting inside the car B, then you will see B at rest and this car A moving at 7 meter per second forward, and you will see the trees also move. So with respect to B, the trees will move at a velocity of 3 meter per second towards the left. and with respect to A, the trees will move at velocity of 10 meter per second towards the left. This holds for relative acceleration also. This holds for relative acceleration also. Relative acceleration, or that is acceleration, say the acceleration of A with respect to B, WRT, or the acceleration of A relative to B, is given as acceleration A, for acceleration small a slash B. A with respect to B is acceleration of A minus acceleration of B. If it at all has any acceleration, then this is the relation. Now so now we'll take up a problem on this. Now we'll take up a problem. That problem, remember one problem, that overtaking problem, right? I mean that this is a police jeep, a police car, and this is a bike. They are at a distance d. Okay. Problem is that the car moves with constant velocity u. It's shown here u. Now when the car is distance d behind the cyclist, motorcyclist maybe, right? Then he starts, I mean the cyclist, he means the cyclist starts to move from rest with uniform acceleration A towards right. So it has at start velocity is 0 and it will have a constant acceleration A. Now you have to find condition so that the car can never be able to catch the cyclist. This is the problem. Find a condition so that the car can never be able to catch the cyclist. Okay. So before solving it with relative motion, we will solve with the usual method. Though I have done it before, still I'll just do it again, solving by the usual method from ground frame. So the method to solve it it's like this: let after time t the car catches the cyclist. Now our whole plan is like this. So you will get an equation in t, and the solution of the equation will not be real. If car cannot catch the cyclist, t will not have real solution. That's the whole plan behind solving the problem, right? If the car cannot catch the cyclist, t will not have real solution. Okay, so we assume that after time t So after time t they are at the same place, the car and the and this cyclist, the thief in the cyclist, are the same place. So it starts from rest, so this distance is half a t square, and the distance moved by the car is ut, and this is obviously d, and from the diagram you can frame the equation. It is done in the diagram itself, the equation, that it's ut equal to d plus half a t square, implies half a t square minus ut plus d is equal to 0, implies t equal to minus c plus minus root over of b square minus 4 and then 2ad by a. Okay, whatever this, obviously you should not worry about this plus and minus sign. For t not to be real, for t not to be real, why? T not to be real means the car cannot catch the cyclist, then the discriminant u square minus 2ad should be less than 0. So that is, the condition is that u square is less than 2ad. If u square is less than 2ad, then the car cannot catch the cyclist. Now this is the condition we have solved by this method from ground frame. Now we will solve by relative motion method. So the alternate solution by relative motion. Okay, so there it is, the car and the cyclist. Okay, so I'll prefer to look from the viewpoint of the cyclist or the car, whatever you choose, whatever, it's up to your choice. So I'll rather choose the cyclist. For this problem I'll choose a cyclist. So for the car, the initial velocity of the car, say name this car 1 and this has 2, so u1, what is u1 equal to u, what is a1, a1 is 0. Okay, u1 is initial velocity of car, acha, u2 is initial velocity of cyclist, acha, a1 is acceleration of car, similarly a2 is acceleration of the cyclist. Okay, so u2 is equal to 0 and this a2 is equal to a. Okay, so now let's let us observe from the viewpoint of the cyclist. That is what we have decided. Now now all is with respect to the cyclist. Now with respect to cyclist, the initial velocity of car and the acceleration of car. See, always remember that I have written it with respect to cyclist, so it's not with respect to ground. It's all the things we'll write with respect to the cyclist. Okay, so with respect to cyclist, the initial velocity of the car. Okay, so as with respect to cyclist means 2, so it's u1 with respect to 2 equal to u1 minus u2. So it's u only. Acha. Now see, acceleration a1 with respect to 2. 1 means the car. So acceleration of car with respect to cyclist equal to acceleration of car minus acceleration of cyclist. So that's a1 is 0 and a2 is a, so that's minus a. So that means the viewpoint is very clear that with respect to the cyclist, with respect to the cyclist, with respect to the cyclist, you see, obviously with respect to cyclist, cyclist is at rest because it is the frame of reference. Cyclist becomes the frame of reference. Now see, we have chosen positive direction along the right. So with respect to the cyclist, the car starts with a velocity u and having an acceleration a towards the left. Minus a means it is having acceleration a towards the left. So with respect to cyclists, the car, if it doesn't collide with the car, see, they meet each other, the car catches hold of the cyclist means they have to be in the same place. So with respect to the cyclist, the car is moving, and if it starts with a velocity u with a retardation a. So if it does not catch, if it cannot catch, then obviously it has to have a stopping distance, right? That means this is the path of the car with respect to the cyclist, that is in initial velocity u, then acceleration, so it has to come, stop, and then return. So that means this stopping distance is, see, this distance was d, the distance between car and the cyclist was d. So here so all with respect to cyclist, the stopping distance of car is should be less than d for or to satisfy the given condition. Satisfy the given condition. So we can calculate now the stopping distance. So cyclist is the frame of reference and cyclist is at rest. Obviously the frame is at rest always. So the car traveling with the velocity u has a retardation a, so it has to stop before crashing onto the cyclist from the frame of the cyclist, obviously. So that's the stopping distance should be less than d. So let us calculate the stopping distance. So the car will be at rest, so we'll put v equal to 0 and use this v square equal to u square plus 2as. We'll use that formula. See, here this a will be minus a, right? So that with this is a formula we will use to calculate the stopping distance. That means put v equal to 0, u is equal to u, and acceleration equal to minus a, and that displacement is equal to s, the stopping distance. So it will be 0 square equal to u square plus 2 minus a times s. So s equal to u square by 2a. So this s should be less than, so u square by 2a should be less than d, implies the condition gives you u square less than 2ad. So this is the same condition we have solved from the ground frame. Now this method of relative motion, this holds for 2-dimensional, 3-dimensional motions also. This v, suppose anything b moves with a velocity vb A moves with a velocity say va there, va. So it's in 2D or 3D motion, whatever. So velocity of B with respect to A, that means relative to A, velocity of B relative to A, you can write like this, VB with respect to A. Now we will write with a vector sign, so it's VB minus VA. Okay, VB minus VA. And again same thing holds for this also. The acceleration of B with respect to B with respect to A equal to acceleration of B minus acceleration of A. Now here remember, VA, VB, acceleration of A, acceleration of B are velocities and accelerations, of A and B from ground with respect to ground frame. These all are with respect to ground frame. It comes from the fact that, see, if you suppose this is let's draw this vector, position vector. So this is RA, RB, I'll explain it in a while, RB/A, and this is the ground frame, and this is the X, Y and Z axis. This is the ground frame, right? This one. A frame is a set of coordinate axes. So this frame is ground frame, and what is this RA? RA is position vector of A, position vector of A. RB is position vector of B. I mean, if you don't mention with respect to the frame, that means it's with respect to ground frame. So RA, position vector of A with respect to ground frame, RB also with respect to ground frame. Now RB with respect to A, that is position vector of B with respect to A. Now the velocity is rate of change of the position vector, dr by dt, that is known to us. Now we'll use that concept. Now from that diagram, from this diagram, right, this diagram, so I can apply triangle law. See, this plus this equal to this. So by the triangle law, RA plus RB with respect to A equal to RB. So now I'll see, this is the triangle law, that this vector plus this vector is this vector. So now I'll differentiate with respect to time. So dRA dt plus drB with respect to a dt equal to drB by dt. So this is what? This is dRA by dt is velocity of A. Now plus this is velocity of say B with respect to A, right? Because it is R of B with respect to A. position vector of B as seen from A. That means you have to construct one. It's like this, na? Constructing a moving reference frame at A equal to RB by dt is VB. So here you go. So again you can differentiate with respect to time. So this is what? This is the acceleration of A. This is the acceleration of B with respect to A. This is acceleration of B, right? So now these all equations, this equation if you write in this way, so VB with respect to A is equal to VB minus VA. Now this equation is acceleration of B with respect to A equal to acceleration of B minus acceleration of A. So these are the equations. Now we have generalized the equations for 2 and 3 dimensional motion. So this is the equation of relative velocity, and this is the equation of relative acceleration. Now this a VB with respect to A is what? VB with respect to A is, now this is velocity of B with respect to A, or it's velocity of B as seen by A. Now this is also acceleration of B with respect to A. So this is a very powerful tool for solving problems, the method of relative velocity.